So the second lecture, I'm going to talk mostly about density functional theory and a little bit about composite methods. And I said at the end of, in the introduction last lecture, density functional theory is just a completely different way of thinking about getting energies and solving the Schrodinger equation. Instead of working with finding the wave function, you try and find the density, which is more or less the square of the wave function. And composite methods, it's a way to try and get high accuracy by putting together lots of different pieces of calculations. All right, so let's think about density functional theory. What's it good for? It's really good for geometry searches. Actually, I did a little test, and I'm going to show you later. The one density function I chose to test, it appears that the density functional theory geometries are better than coupled cluster triple zeta geometries in some kind of comparison over 100 or so geometries. I found that interesting and remarkable. It's really great also for vibrational frequencies. The cost of doing a DFT calculation compared to a coupled cluster triple calculation is orders of magnitude less. Yes?
Out of curiosity, what do you mean when you say geometry search? Are we talking about the geometry of what?
Okay. In general, if we're going to do, I'm sorry. His question was, when you do a geometry search, what do you mean by a geometry search? All right. So when we do kinetics, you need to find a partition function for a transition state and a partition function for a reactant. Partition functions we get generally at the first order approximation by doing a rigid rotor harmonic oscillator analysis about the minimum point on the potential energy surface. The potential energy surface being this solution to this electronic Schrodinger equation. And so a geometry search, you're trying to find the minimum geometry. The geometry has the lowest potential energy with respect to nuclear variations. Okay? And you do that for the reactant. And then for the transition state, you do a geometry search is with one additional constraint, and that is that one of the second derivatives should be negative rather than positive. Right? So geometry searchers are finding the minimum for the reactant and the minimum with this constraint. To do these rigid rotor harmonic oscillator partition functions, you need to do vibrational analysis. You need to have vibrational frequencies. You need to have rotational constants. The rotational constants come directly out of the geometry search, the structure. And the vibrational frequencies come from taking the second derivative of the potential. You simply diagonalize the Hamiltonian for nuclear coordinates, and that gives you vibrational frequencies. So you just have to take the second derivative of the potential, and that gives you the frequency. And that can be done analytically in density functional theory with many codes. And that greatly simplifies things. Or is a magnitude faster to get a vibrational frequency with DFT. And again, it's not clear to me. I couldn't do the same quantitative test, but I did a bit of a test, and I'll show you. It appears that DFT has comparable accuracy for vibrational frequencies to coupled cluster. And coupled cluster, remember, is called the gold standard. Sorts of 10% accuracies for partition functions is probably a reasonable guess, maybe even 5%. Using density functional theory to get absolute energies is more troublesome. There's made great progress in how good the absolute energies are, but it's not still to my desired accuracy. Maybe for many cases it's still okay, but it's not the same as a good coupled cluster exploration. The disappointing thing about density functional theory is once you pick one functional, you get what you get. You can't systematically improve it. You can't do a little bit of exploration of that, of this thing you're ignoring, you do a little exploration of that other thing you're ignoring. It's just whatever number you got, that's what number you got. If it doesn't agree very well, you got to go back to the guy that made the density functionals and tell him, you need to improve your density functional. Well, that doesn't work, of course, you can't. The people that do develop them are continually trying to improve them, but there's no sort of back and forth between and user ability to improve. There are lots and lots of functionals. That's the other bad thing. It's a real nightmare trying to figure out which functional you should use. I've got a few of my favorites. You'll probably all develop a few of your own favorites if you do any calculations. But what is your favorite? What should be your favorite? Probably depends a little bit on what problem you're trying to solve. I'm always trying to solve kinetics, so I have certain things that I find are useful for kinetics. Other things might be useful for other things. B3 lip was sort of the start of the revolution in my mind. At least when I was just getting started as a young faculty member, there wasn't really anybody doing density functional theory calculation in chemistry. They were doing some in solid state stuff, but not in chemistry, not in gas phase chemistry. Until Becca came up with this B3 lip functional. And it was just so much faster than anything else, and so much and so much better than essentially anything else that everybody just started using it. There's one problem with B3 lip. It has no dispersion. I don't know if you know what dispersion is, but dispersion is an important feature of interactions that determines their long-range interactions, determines basically the structure of van der Waals molecules. That might not sound very important, but it really is when you're trying to get accurate understanding of orientational and sort of details of your structure. So I still use B3 lip to sort of do quick and dirty explorations of potential surfaces, but only when I'm looking at parts that I don't think it's going to give me trouble with. Another more recent density functional is something called B2P lip D3. They're all just acronyms probably to you, and I don't want to take too much time to describe the acronyms, but there are little pieces I want to describe. D3 means that you're putting in somebody's third version of dispersion correction. They've figured out how to put in dispersion corrections. And that makes a huge difference in your ability to treat low barrier processes. B3 lip will almost never find something if it's got a barrier that's below the asymptotic energy. It will just say there is no barrier. And it'll be wrong, but it'll just keep telling you that there's no barrier. It's because it doesn't have dispersion. Now, you could just add dispersion to B3 lip, and that's actually not necessarily a bad approach. I haven't explored that. But B2P lip does some other things that make it better. But at the same time, those other things make it quite a bit more costly. And this is the functional that I'm going to show you, geometries that are comparable to couple cluster. The cost of this is comparable to MP2. B3 lip's cost is more like Hartree 5. So that's why people still use B3 lip. But the reality is, if you try to do a post-Hartree 5 calculation and get a good energy, the cost of doing a B2P lip is sort of minimal. You can do some. You can just use B2P lip after you've already found that with a less costly method, and it's pretty simple. Another good standard, one that I've tried and that seems to be sort of, in my mind, is sort of the replacement for B3 lip, is something called MO62X. It's not as fast as B3 lip. I don't think it's quite as accurate as B2P lip, B3. But it does find processes that have no barrier. It is a lot more accurate than B3 lip. And even sometimes it's even slightly better than B2P lip, but not usually. This functional is developed by Trular. This one is developed by somebody named Grimm. And this, as I said, was developed by Becca. All right, so what is density functional theory in 2 minutes? As I said, it starts by thinking about the densities. There's two theorems that are called the Hohenberg-Kohn theorems. First is that the ground state properties. Remember, we're really interested in ground state energies. That was how we started with when we talked about the electronic Schrodinger equation. And we just want to get the ground energy, because that's really what determines chemistry generally. The ground state properties are uniquely determined by the density. So if we focus on the density, we can, in principle, get the right answer, just like we get the right answer when we focus on the wave function. And then they went ahead and defined the energy function in terms of the density and showed how you could variationally minimize this functional to try and get that energy. Well, those are great mathematical sorts of theorems, In practice, you can't do that. You can't really do a variational minimization to any kind of truly quantitative accuracy. But you can get useful empirical representations. And so density functional theory ends up being all sorts of empirical approximations to try to get something that gets close to being the proper variational minimum representation of the density. As I said, B3-LIP was this first one. Not only, it's one of its features of it being popular was it was available in this Gaussian code that I mentioned the other time. I mentioned Popo got the Nobel Prize in '98. He actually split it with Kohn for these DFT developments, these theorems, and other work. The B2P-LIP and B3-LIP are what are called hybrid functionals. They're a combination of density functional theory and Hartree-Fock. So you kind of take like the best of both worlds. You do your wave function calculation and a density functional theory calculation. Look at that number of citations. 62,000 citations for a paper published in 1993. There aren't many papers out there that have anything like that number of citations. Essentially, anybody that has run an electronic structure calculation has run a B3-LIP calculation. Maybe that starts to be less true now. Maybe people don't bother to do B3-LIP anymore. I don't know. But for 20 years, that was true. All right. People that do DFT have defined this thing that they call Jacob's ladder. This comes from the Bible. I'm sorry. It's just the way it is. The idea here is that Jacob had started building a ladder up from earth to heaven. And they like to correlate this progression of density functional theories with that progression from earth to heaven. They call them different rungs of theory. In this plot, this is from Martin Head Gordon, they call the heaven chemical accuracy. Chemical accuracy means accurate to within 1 kcal per mole. I don't think that's heaven. I think that's maybe somebody's old view of heaven. We can do a lot better than that nowadays with lots of things. And even density functional theory is getting beyond that for a lot of aspects. But anyways, you get the point. You're trying to go from Hartree-Fock down here on Earth up to really high accuracy with better and better density functional. Original density functional theory work was called local density. They made what was called the local density approximation. That just depended on the density. They just thought about the absolute value of the density and tried to figure out what the best. That was basically useless, and so at least for chemistry. For solid state, I guess there was still some utility for a while. But the next step was to make what were called generalized gradient approximations. And that was, now you think about how the gradient of the density, how the density varies with nuclear coordinate. And with that, they started to get quite a bit better. And that was the foundation of B-LIP and BP. You can see from that name, B-LIP. Well, that sounds a lot like B3-LIP, doesn't it? So this is like a precursor to B3-LIP. And then they started to worry also about the dependence on the kinetic energy density, not just the overall density, but the density relevant to just the kinetic energy. I don't really know much about this. They call those meta-GGAs. The real progress was starting to do things with hybrids. Hybrids, again, you're mixing wave function theory and density functional theory. So you got Hartree-Fock and DFT. So here's our B3-LIP. This omega B97 XV is something from the Martin Head Gordon group. MO62X, I said, is a good replacement for this. Now it's not just a hybrid GBA, it's a hybrid meta-GGA. Okay, and that really is a step beyond what B3-LIP is. MO62X doesn't have dispersion, but it sort of does. I don't quite understand how it works, but somehow it sort of does. But there's debates back and forth about whether you can do MO dispersion. The next step is to have double hybrids. Well, what do I mean by a double hybrid? Now we're going to have a Hartree-Fock treatment and an MP2 treatment and a DFT treatment. And that really is the big step. They didn't put B2P-LIP in this plot, but this is where B2P-LIP D3. And actually, B2P-LIP D3 is probably not the best double hybrid. why do I use it then? Because it's the one that's in Gaussian. Probably if I knew what I was doing, which I don't really, I could implement some of these other double hybrids that might be better. And I'll show you some of why I say it's not really the best, apparently. But it sure is a lot better than B3 Lip, and apparently quite a bit better than MO6 to it. So again, pretty good numbers of citations here also. These are from papers in 2008, 2010, 5,000+ citations in 10 years. Wow. One of the common things that people that build density functionals like to do is to test them. You know, you've got all these parameters, and well, maybe this is just, at some level, it's just an optimization game. You've got some kind of large-scale parameterization, and so the more parameters, the more observables you're parameterizing against, the better you'll do. And after you've done that parameterization, you should have some tests that are outside your parameterization set. And so these people worry about that a lot. Actually, one of the people that's moving forward in that sort of direction a lot is Martin Head Gordon. And he's looking at things where you've got, you know, like 1 million parameters to parameterize and trying to find nonlinear optimization. And you actually has some kind of exponential explosion of number of parameters. And you get into all sorts of neat nonlinear optimization games. In the end, though, you want to compare against sets that you didn't parameterize against, and that's these. And this particular, Grimme, who developed the B2P Lip, developed a nice set of data points to compare against. So he's got 841 data points. I'm going to show some of his comparisons of different methods to give you a sense of where we're getting. So these are, remember I showed you Jacob's ladder. These are the different rungs on the ladder. If you start with LDA, you got about 12 kcal per mole accuracy. And there's multiple different methods, and he's averaging over some of these different methods. And you see the progression. Once you put in the derivative of the density, you get a dramatic improvement in the accuracy, more than a factor of 2. Meta GGA, a little bit of an improvement. Hybrid, you're getting close to a factor of 2 in there as well. And what does this say? B3 Lip D3 is right about in that hybrid average area. Double hybrid, another factor of 2. Okay, it cost us some money. We got now the cost of an MP2 calculation instead of a Hartree-Fock, but MP2 is not that expensive. One can readily do MP2 calculations on combustion size systems of practical interest. This is another comparison. This is a comparison for different types of double hybrids. So as I said, B2P Lip is apparently not the best one. This doesn't have a D3. I don't know. I think it did actually include it, but they just didn't bother to list the dispersion corrections. And these are some various other ones. Looks like this DSD B-Lip would be a better one, but I don't know how to implement that one, so I don't. But these numbers here are kcals per mole, 2 kcal per mole. Chemical accuracy is 1 kcal per mole. So we're not quite chemical accuracy, but we're a lot closer than we were back when we started with local density approximations or even meta GGAs. I meant to say one thing here. If you think you could make a similar kind of progression with Hartree-Fock, with single reference-based methods, standard wave function theory-based method. Hartree-Fock has an accuracy of about 10 or so kcals. I don't know what the number is, but it's on the order of 10 kcals at least. MP2 would probably be somewhere in this region. CISD might be somewhere in this region. CCSD parentheses T is somewhere around here. Probably a little better. It's probably more like 1.5 kcals if you take the CBS limit and you're talking about 2 sigma errors. I don't know what they're talking about here. Probably it's just the average, which is so a couple clusters. CBS is maybe half this is my guess once you compare them properly. But you have the same kind of progression as you go through level of expense and so on. But to get to 1.8 kcals with wave function based things is much, much more costly. This is just showing you the importance of including this D3 empirical dispersion correction. All the sort of sets of 4, the 2 on the right always are the same as the 2 on the left, but including the dispersion. You also see that there's now a dependence on basis set. Bigger basis sets means shift to the right one in these. And so you get better results with bigger basis sets. One of the beauties of DFT was that you could use really small basis sets and get good numbers. You lose some of that, though, when you go to these hybrid methods, because now you've got some component that's wave function based, and the wave functions have a big basis set dependence. And so I used to always say, hey, it's silly to do if you're doing B3 lip to do anything more than 631 G star or maybe 6311 plus plus, because it's just noise. It was parameterized for the smaller basis sets. It wasn't parameterized for the bigger basis set. And you don't have any kind of convergence with basis sets. That argument goes to the wind when you start talking about double hybrids where you've got wave function components. This is just a slide showing you the different things within the different sets. So you've got your different rungs of Jacob ladder going to the right, getting better and better. And this is only some small fraction of the possible. You could, everybody and his dog can make, you could go home in a day, make your own density functional, and then go and start comparing. Gaussian will let you put in random parameters for all the different components, and you could try to win the game and get the one that has the highest accuracy and get your 10,000 citations. It's quite an easy problem. All right, so now how good are these geometries? I decided to test it by comparing B2 PLIP D3 triple zeta with coupled cluster triple zeta. Coupled cluster triple zeta, I said, is a gold standard. It's actually not completely converged with respect to basis set size. I would have been better to do this test with maybe a quadruple zeta F12, but I can't afford that. I could have maybe afforded a TZ F12, but I had a database of these geometries sitting around. And so I could easily compare them. Right? And so I've got a set of 150 molecules, more or less, with the coupled cluster triple zeta database. I run that whole set with my B2 PLIP D3, same basis set. As I said, orders of magnitude less CPU. And then I just compare the energy for the CBS limit for a good coupled cluster F12 calculation. Valence quadruple zeta F12 calculation is basically the CBS limit. The energy of the geometry is a measure of how good the geometry is, right? Your optimum geometry should have the lowest energy. So if you got two geometries and one has lower than the other, the one that's lower is your better estimate for the true geometry. And the proper test, you should have a really good energy. Well, this is a pretty good energy. You could do a higher test, but it would be more expensive, right? So here, the average value of this energy difference is negative. If it's negative, that means that the B2 PLIP geometries were actually on average better than the coupled cluster. The maximum difference was positive, and the minimum is slightly negative. So there's some, basically, I read this as saying, I should have reported this root mean squared deviation, or yeah, I didn't, anyways. This is basically saying these two methods give very similar geometries. You would not get this same result with B3 lip or with MO62X. You would not have a similar level. Another test is to look at the frequencies. How good are these frequencies? Again, I presume these frequencies are accurate. And this is a bigger presumption than it was for the geometries. I know that the frequencies change by a few percent going to quadruple zeta always, and sometimes 5 or even 10%. Sometimes you get even larger, but they're probably not converged to better than about 5 or 10% on average. But still, let's compare what we get. And how do we compare frequencies? One simple way to compare them that I sometimes do is just to take the product of the frequencies. At high temperatures, your partition function, classical partition function, is just the product of frequencies times some prefactor. So qualitatively, you just look at your product frequency. a better thing to do is to actually evaluate the rigid rotor harmonic oscillator partition function. Well, I'm just going to evaluate the harmonic oscillator part. I already showed you the geometries are good, which comes into the rigid rotor part. So I just took the partition function, put Q equals sum on I of e to the minus beta EI, and I did that for all of the modes, and then evaluated the partition function as a function of temperature for these two methods for a few sample molecules. What molecules did I pick? I picked a molecule for which, a system for which I could do coupled cluster triple zeta, which isn't all that many, but that is of relevance to combustion. What's of relevance to combustion? Low temperature combustion. You're interested in the RO2 to QOH transformations and the RO2 energies and partition functions and the partition function for the transition states. So this is a particularly simple illustration of the relevance for low temperature combustion kinetic evaluation. Right? So I've got my RO2 species. This is just methyl CH2O2. My R here is ethyl. All right? And then I've got the QOH for that. Now it turns out this QOH is not of any importance in the real world, but it's still, the question of how you do it is perfectly relevant. It still has all the same electronic structure features. It's just that the energy comes out high, so in the real world it doesn't come into combustion. But it's still a good test because it's exactly the same electronic structure features. Then another thing that happens sometimes that we're kind of curious about is if you transfer an O to, or OH from one side to the other from your QOH. So here's the transition state to go from the RO2 to QOH, the transition state to have the HO2 loss from the RO2, which is a standard thing, and then a transition state to have loss of HO2 from the QOH, and a transition state for OH loss from the QOH. And then just for your reactants, ethyl plus O2. And I'm just looking at the ratio of the two partition functions. If the two things, if we take this as our norm, as our absolute value, then we want values near 1, and then that would mean that we have perfect agreement. And mostly we get pretty good agreement. Certainly if we go to sort of 800 and higher and ignore this one case, we're within 10, 20% for all of our cases. And I don't know which one's right, which one's better. But they're completely different methods giving us very similar numbers, even for the transition states. The transition states are more difficult to find geometries and frequencies for, so that's encouraging that it includes that. This one is a bit bad. Which one was this? This is this transition state here. If I remember right, there can be a large, I think half of this difference is because of a difference in the torsional frequency. Differences in torsional frequencies are not as problematic as differences for other frequencies, because at high temperatures, the partition function for a hindered rotor goes to that for a free rotor, which is independent of the force constant. All right? And so if you have a 10% difference in the force constant, you don't care. It maps into no difference in the partition function. Oh, I think there was also a sign when I looked at this that this basis set is not converged with respect to the basis. How do I know that? There's a big change from the coupled cluster double zeta and triple zeta. I haven't done quadruple zeta, but if there's a big difference between triple and double, then you expect similar sort of difference between triple and CBS or quadruple zeta. But qualitatively, it looks like about 10-20% is the sort of accuracy one can expect with that. I'm not going to try and tell you this is the way you should do your electronic structure calculations to calculate rates. I'm going to, as you've been seeing, make suggestions of what I like to do. But every person has his own different computational resources and different desire for accuracy and different size system they're looking at and so on. The message you should take home for yourself is that you can devise your own method that suits your resources for any problem that you're looking at. It's not hard to do, and there's no reason not to do that. There's a good book describing that, and this is one of the great values of the Gaussian program, is they basically told you how to do this. They tell you about exploring chemistry with electronic structure methods. I would highly recommend reading something like this as a companion to starting out to do electronic structure theory calculation. So you understand what all this acronyms and why we put all these different methods together and how you choose for yourself what is the method of choice for your problem. Eileen Frisch is the, I presume, wife of the main author of Gaussian, although I don't actually know that. Something that I commonly do to get things working is I'll start with a B3 lip geometry. So this is my protocol, as they like to say. And then if I'm thinking that I'm going to be doing a process that has a low barrier, oftentimes I'll know that, and I'll say, okay, I know there's a low barrier, so I'm not going to start with B3 lip because it's just going to fail. Then I'll start with MO6 2x instead. I'll find the transition state with that low-level method, small basis set, maybe 6 through on G star. And then after I've optimized and found the transition state at that level, then I'll say, okay, now I want to get a better geometry. So now maybe I'll go to this B2 plip D3, refine the geometry, redo the frequency analysis, use that as the input for my rate calculation, my master equation calculation. And then I'll take that geometry and I'll try and get a good final energy for that thing, because the energy is one of the central things that comes in to the analysis. As I said at the beginning lecture, Carlo Cavallati has written a code for automating this particular sequence. This particular sequence, not with any method. You can put whatever methods you want at each of these stages, just that it has a first stage where we optimize at a low level, second stage we optimize at a higher level, third stage we get a better higher accuracy energy estimate. That code is supposed to be available on this website, but I'm too slow, and so I didn't quite make it in time for this to do that. But hopefully within a week to a month, that code will be available for anybody to download and use. It's basically coupled to Gaussian and MolPro as codes to use to do things. When you try to get high accuracy energies, high accuracies, what you're trying to do is really go in two different directions. You try to go to larger and larger basis sets to get to this complete basis set limit, and you try to go to more and more numbers of electrons treated as in your post-Hartree-Fock evaluations. You try to get higher and higher electron excitations in your analysis. To get a good absolute energy, to get the true energy, you have to go to full CI with an enormous basis set. You can't do that. Just not feasible for any real problem. So what people will try to do, what people will do is they'll say maybe go to really close to the full CI limit with some small basis set, and then do something like a Hartree-Fock calculation with a really large basis set. That would be the first order approximation you could make. The problem with that is that you're making a separability assumption. You assume that the basis set differences add to the methodology differences. That's not a bad assumption at some level, but it's not a great assumption. So what you're better off doing is, in addition to doing this Hartree-Fock at the CPS limit, maybe you should do the MP2 at slightly lower limit, and then do a CCSD parentheses T at a slightly lower limit, and then do a CCSD T parentheses Q at a lower limit. And then you can make what are basically small steps along this diagonal, and your separability assumptions become less problematic. What I just described to you is the basis of almost everybody's high-level electronic energy evaluations. They couple together a series of different attempts to get to the CBS limit. Another word for that is something that Wes Allen calls the focal point analysis. And you try to have as few possible assumptions in getting as close as you can to the full CI and CBS. So these are what have been, there's a whole bunch of standard composite schemes. It's a little bit like DFT. You have 100 different methods that everybody has as their favorite. And the people that developed Gaussian, and Popel, I guess it's more precise, Popel developed a whole series of methods and gave them a name, and he called them G1, 2, 3, 4, and then he stopped at G4. Why did he stop at G4? Basically, he'd reached the limit of how accurate he could get with the kinds of assumptions he wanted to make, the kinds of limits of the calculation he was willing to do in his analysis. G4 is a great method. It really does have chemical accuracy. It has on the order, 2 sigma on the order of 1 kcal per mole, maybe 1.5 kcal per mole. It's very efficient. You could, I don't do these calculations very often, but you could, I believe, reasonably do C10, C12 sorts of molecules in modest amounts of CPU. For some reason, this is one of my pet peeves, one of the favorites in combustion is CBS-QB3. CBS-QB3 is like GN, but it's smaller basis sets. The basis sets it uses are because they're smaller, do not have the same level of accuracy in the approach to infinite. There are some things that it tries to do better, which is to think about unrestricted spins and so on. But when you look at the accuracy of this on a large set of combustion relevant species, it's not the same as this, as I'll show in a minute. Another nice thing to do is something called bond additivity correction. All these methods, these methods here have some kind of correction to try and make it so at least their average error is 0. They try and count for spin differences and how methods fail for different spins. Melius, who used to be at Sandia, I think he's at Lawrence Livermore now, came up with or really popularized something called a bond additivity correction. And with that approach, you count how many bonds you have of each type, and you can make a correction based on each different numbers of bonds. And you can get, with things like MP4, you can get qualities that are almost like some of these higher level methods. Franklin Goldsmith, Bill Green took this idea and applied it to coupled cluster evaluation, or more precisely QCISD parentheses T, which is just another version of coupled cluster. And that turns out to give nice high accuracy. Oops. What I'm going to tell you next is we can go now to methods approaching 1/10 of a kcal per mole accuracy, but they're a lot more expensive. Different people call this different things. Focal point, John Stanton by Wes Allen. Heat is a method from Stanton, named for Stanton. Martin is called WN. W4 is the most analogous. We developed our own method. We call it ANL0. We start with coupled cluster triple zeta optimizations and frequencies. What I just showed you, maybe I should have just done B2 PLIP D3. But anyways, this was before. We started this project a long time ago, 5 or more years ago. I can be very slow at times. And we then, the reason for doing this is we want to get these frequencies right. We want to do kinetics. We want to get the partition functions right. We don't just want to get the ground state energy. What I'm going to show you here is just the ground state energy. But if you really want to get frequencies right, and actually frequencies matter in getting high accuracy heats of formation because they determine 0 point. And actually the 0 point is one of the more difficult things to get accurate now. It's probably the biggest uncertainty in the end of the approach that I'm going to tell you about, is getting the frequencies right, getting the 0 point energy correct. Then we get our CCSD CBS limit by doing augmented quadruple zeta, augmented quintuple zeta. We also did something where we did F12 and up to quadruple zeta. More or less the same results. Slightly better apparently with this, but more or less the same results. We then add in corrections. We put in a T parentheses Q correction. Remember I said we can go to higher order in coupled cluster. Now we can only use the double zeta basis for that, but it's a correction. And so it's like back on that diagonal. It's just a one more step on the accuracy in the diagonal. We deal with the core valence interactions. Again, we try and get to the CBS limit with coupled cluster and treating the core valence interaction. We try to deal with anharmonicities. Anharmonicities are a big part of your 0 point energy. People try to sort of treat those empirically, and that's not so bad. But you can do spectroscopic perturbation theory routinely with codes like Gaussian and do quite large size systems. There's relativistic effects and diagonal Born-Oppenheimer correction. We talked about the Born-Oppenheimer problem. Well, you can account for failures of the Born-Oppenheimer approximation to some level. What this plot shows you is how important each of these different corrections are. The T parentheses Q correction, on average, it looks like it's about -2 kilojoules per mole, about half a kcal. No wonder you can't decrease yourself much below a kcal when you get to the end of it, because none of those methods are including this correction. Similarly, none of these methods are including core valence corrections. None of them are including anharmonicity corrections in other than very crude fashions. And so we've got 3 separate corrections, each of which are a half a kcal per mole sort of accuracy. 2 sigma is a kcal. We have problems then trying to wash all of that into some simple parameter. But we can evaluate these things. And if you look at sort of the convergence of these things, you can go slightly higher. And it seems like these things are probably converged to about 1/10 of a kcal sort of accuracy, if you look at how well we converge each of these separate pieces. So then we can compare them as well with experiment. At Argonne, somebody called Branko Rusic has invented what he calls the active thermochemical tables approach to thermochemistry. Well, the standard idea in thermochemistry is you get some experiment and you measure some energy relative to some other species. And you get then a ladder of thermochemical values that depend on everything else in your ladder. What Branko says is, well, you shouldn't just build individual ladders. You should connect all of your measurements together and make the heats of formation be the best self-consistent set with all those measurements. He ends up then with a table with tens of thousands of determinations, optimizes that table with fancy mathematics, and gets then the best estimates and corresponding error bars in those calculations. It turns out that for this, we were trying to do sort of all the core combustion species. This is basically the same set as what Franklin Goldsmith did in bond additivity corrected things. And it's a large set, and a lot of those species are in Branko's table, maybe half of them. But some of them still have large error bars in Branko's table. And so what it turns out in the end is that our error distribution has this mean and deviation. But it's not clear that it's actually perhaps even better than that, because there's a significant component of this that comes from the uncertainty in the active tables value. But anyways, we're at the order of 2 sigma of about 3/10 of a kcal at least, maybe better with this. It's very costly though. We can't go beyond 34 electrons more or less. 34 electrons takes you to about 4 or 5 heavy atoms. Things like butane are more or less the limit. But it's a good benchmark. And so we can then test different methods against this. Furthermore, it gives us a way to basically nail all of our core species. Remember we talked about the mechanisms at the beginning, how you've got hierarchical mechanism development? Well, this then will give us all the basic components of our standard and most important species with very high accuracy. Another thing it does is there's certain classes of reaction that happen in combustion. We'll go into that a little bit later, but there's abstractions, there's RO2-QOH chemistry, there's addition reactions and so on, and there's additions to pile. We can have then a good high accuracy treatment for basically all the prototypes of all the classes, which is what we're working towards. And then we can use that to test other more approximate methods to see how accurate we get. Here is a plot showing the Boltzmann factor in a 2 sigma error for different methods. You see here, this was our ANL0 method. This is a G4 method, a 2 sigma of about 1.1 kcals. The 2 sigma for CBS QB3 is twice that, about 2.5 kcals per mole. So then if you look at the errors that you're making, just from a Boltzmann factor in that, you get pretty significant errors. If you're doing low temperature chemistry, you're interested in about 800 Kelvin sort of range, factor of 5 sorts of error. That's getting to be large enough that it's hard to argue that you're doing better than any kind of empirical model that you're going to do to estimate a rate constant. G4 reduces that by about a factor, by about the square root. And by the time we get to ANL0, we've got 10, 20% sorts of error bars. And so that shows you why I like to claim that we can get pretty good rate estimates. You'll see some rate estimates that have that kind of apparent accuracy later as we get to the kinetics part. This is a nice approach, the bond additivity corrected CBS approach. It's a little bit worse. It's 2 sigma is 0.58 versus 0.32. So it's somewhat worse, but it's small enough that you're not making too bad an error in your rate estimates just as a result of that energy. The one unfortunate thing is this is defined only according to the number of bonds. Well, what happens when you have a transition state where you're halfway between one bond or another? What is your bond additivity correction then? I think one could define things quite reasonably by taking like the proper weighted average of the transition state relative to your reactants and products, and then you could count how many bonds you have in each one and do some kind of weighted average of those. That hasn't been done, but I suspect it would work very well, and that would be a good way to generalize this approach to then let you do bigger systems. Those are the kind of tests we need to get to and start doing. I think I'm going to stop there for now. I think we've gone on long enough again. Oh, no, wait. What time was I supposed to? Wait, I'm supposed to stop 15 minutes after the hour, wasn't I? I lost track of time. Does anybody have a schedule? What time are we supposed to end? Nobody has their schedule?
Yeah,
15. Oh, I can keep going for a few more minutes then. I'm sorry. You can suffer a little longer. I don't know how much more. Oh, this is like the last slide. So as I said a few times, it's important if we deal with ions, particularly anions, to have diffuse function. Something that give us problems, and that this is one of the problems that it is Zwitterions. Everybody know what a Zwitterion is? A Zwitterion is a molecule that basically has 2 ions within the molecule. So you have one part of the molecule that's a plus charge and another part of the molecule that's a minus charge. It happens all the time in proteins. It turns out it happens in combustion, and people don't know about it. Combustion transition states we're finding will often have a Zwitterion character that makes it really hard to treat them well. I don't really know the solution to deal with those, to be honest. Lots of people talk about basis set superposition error. And a lot of those comments aren't really correct. But let me describe to you what it means, so then you can judge for yourself what's right. When you take 2 species and you put them together, say at van der Waals separations, then the calculation for species A is going to be able to borrow some of the basis functions from species B. Some of these basis functions sort of extend into the region of the electrons for the species A, and vice versa. And so what you get is you get an artificial lowering of the energy for species A due to its stealing these basis functions. And that's called the basis set superposition error. Now, how they try and correct that is what's called a counterpoise correction. Is they take this, when they calculate the energy of species A by itself, you still put the basis functions from species B there for it, and vice versa. It turns out that whenever you do that, you almost always overcorrect. And you always overcorrect by almost as much as the correction it is itself. If you get to good size basis sets, then the fact that you're borrowing things becomes irrelevant, because you've already got enough basis functions on your thing. And so the CBS limit works perfectly fine, even though there is some of this basis set extrapolate. I suspect, although I don't know, that some of the ideas that you really need to do basis set superposition error comes from the idea that everybody thinks that you always need to have diffuse functions. I personally don't think diffuse functions are useful generally as long as you're doing a triple zeta calculation. If you have diffuse functions, then your basis functions from this second thing extend further into the molecule, and so then there's more of this basis set borrowing. And so if you're always doing diffuse functions, you're always getting larger basis set superposition errors, and that becomes more of a problem. My observations when I do lots of calculation of long-range transition states. My energies, if I look at the approach to the CBS limit, it approaches better if I don't put in the diffuse functions. And the only exception to that is at the first level when you do just the double zeta. When you just do the double zeta, then often it's better to put the diffuse function. And of course, the other exception is when you have an anion. Anions just really need diffuse function. I said before, density functional theory, less sensitive basis sets, but that's one of the beauties of the original forms. We lose a lot of that when we go to these beautiful double hybrid methods. Now we've got basis set dependence back again. People don't realize this a lot. When you want to just run the standard electronic structure codes, a lot of times their convergence parameters are not sufficient to get frequencies, low frequencies, not sufficient to get them within 10%, even 20%, even 30%. You have to ask for higher levels of convergence commonly. In Gaussian, you do that by adding this command int equals ultrafine. In Mol-Pro, couple cluster theory, you got to put a whole bunch of different tighter convergence thresholds. That gives me lots of headaches and so on. If you want to do anharmonic frequencies, now you're evaluating the third and fourth derivatives. Evaluating the third and fourth derivative of something numerically means you have to have very high precision. You get into lots of problems with getting anharmonic frequencies with some of the more advanced density functional theory methods, because they've got all this fitting, and this fitting introduces oscillations, and it just causes havoc in things. And so my anharmonic frequency evaluators I generally do with B3 lip just because it's more stable. And it's just hard to get anharmonic frequencies. It's hard to get third and fourth derivatives of potential numerically. All right, so just my acknowledgement slide again.